Okay, so thanks for coming, everyone. Today we have José Luis Gómez from the Andalucía Institute of Astrophysics here to tell us about the Event Horizon Telescope and future prospects of black hole imaging. So, José Luis, whenever you want.
First of all, thank you very much, Valentin, and the rest of the Institute and the University for the very kind invitation to come here and talk to you about observations of black holes with the Horizon Telescope. This is a very general talk I usually give when I am asked to give an overview of the result. So, and I think for this audience, you may be perhaps more interested in the theoretical part. So, don't hesitate to interrupt me anytime if you like to dig a little bit more into theory of interpretation how we actually came with the Mars or the test of GR or whatever, okay? Because in general, as I said, this is mostly thought for astrophysics. So do not hesitate to stop and ask, okay? So as Valentin said, what I'm gonna do, I'm gonna just give a very brief overview of the Horizon Telescope, the first images of black holes, what we have been observing so far, what kind of tests we have performed so far, and then I'm going to move into what are we going to do in the future. We have already taken images of the two main targets. So what is next for the IAA-CSIC? What do we want to do? What do we want to do in terms of science, and what kind of improvements in the facility in the telescope that we are planning for the next decade. So let me start then with this PR movie that we prepared for the release of the first image of the central black hole in the Milky Way. As you know, this is Valentin, can we get a little bit dimmer the light?
Yeah, can you turn off?
Okay. So this is a zoom in into the center of the Milky Way. These are optical images. And these later images that you are going to see here are taken with the VLTI. These are near infrared images where you can see the motion of actual stars. These are actual stars moving around the center of our galaxy. And this is the modeling of these stars that have been done by two different teams, one in California and one in Germany. And as you can see here, they have been able to track the motion of the stars, and they have measured that there is a very compact object at the center of the galaxy of about 4 million solar masses. And as you know, this was awarded with the Nobel Prize in Physics in 2020. Okay, I'm very happy to say to mention also that the IAA-CSIC image of M87, which was already known, was already released, was mentioned twice in the press release of the Nobel Prize. And it was shared with Roger Penrose half, and the other half with Rainer Gensel and their guests. And I'd like to stress here that the Nobel Prize is for the discovery of a supermassive compact object at the center of our galaxy. They do not talk about black hole, okay? Because and there were no image, and there is no actual proof that it is a black hole. And soon after this, we published the first image, and this is what it actually looks like. And I'm going to show you that it looks really like what we would expect for a curved black hole at the center of a galaxy with a 4 million solar masses. And how is this image made? What is what we are capturing with the Event Horizon Telescope? This is an animation where that shows that if we have the central black hole here, the ring that we are seeing is composed by many different rings, actually by an infinite number of rings. We have what we call the N0 ring, which is produced by the rays that are slightly bent. This N0 basically codes the astrophysics, the accretion onto a supermassive black hole. But then we have the N1, N2 rings, which are rings much thinner, and they are produced by photons that go once, twice, multiple times, and there's an infinite number of rings. These are the key rings. These rings are not affected by astrophysics. So these rings are produced just by the Kerr metric. So if we are able to measure this, we can make very, very strong constraints on the Kerr metric and actually test whether it is a Kerr black hole and actually measure, as I will show in a minute, what is the spin of the black hole. So, and this is the kind of images that we are observing with the Earth Horizon Telescope. And as I said, it's mostly dominated by the M0 ring. And for the case of M87, it's 42 microseconds. And for the case of IA, it's about 52 microseconds in size. And this changes slightly with the spin of the black hole, as I'm sure you all know. So the size of the black hole shadow is usually about 10 gravitational radius, and it's a little bit smaller and for the spinning black holes. And the actual size of these rings changes just by a small fraction of the order of 4% with the spin. So if we are able to measure the N1, N2, or in general the length ring, we will be able to. We are testing actually GR, and we can even get an estimation of a direct measurement of the spin of the black hole. So far we have the images of M87 that we published in 2019, and recently in 2022 we published the first image of the supermassive black hole at the galactic center. Now we have these images from two black holes which have very large different masses. And actually, with these images, we are probing a completely different parameter space and in gravitational potential. In this case, we are when we combine the images from the M87 and SGA with the gravitational wave detections, actually, what we have is that we can test deviation from the Kerr metric with masses that spans 8 orders of magnitude. So this is one of the best tests that we have so far of the equivalent principle of GR, in which the black hole really doesn't. I mean, the only changes that we see in the black hole are due to the mass. So the black hole is fully characterized by the mass and the speed. So how did we get that? How did we get the image? And now it comes a little bit more to the astrophysics. So as you know, these observations were obtained with an interferometric array, which is called the Event Horizon Telescope. This is composed, these first observations in 2017 were obtained with an array with 8 different telescopes in 6 different locations, in Hawaii, in the US, Mexico, Chile, and Spain. And the way it works is that, imagine that we want to take a picture of the black hole at the galactic center. The angular resolution we need, the angular resolution we need is about 20 microseconds, which is the size of a grain of salt seen from the LA in New York. So we need a telescope of the size of the Earth. Of course, we are not going to make a telescope as big as the size of the Earth, so we use telescopes spread around the globe. And how do we obtain the image? So the way we obtain images, we obtain the interferometric pattern between a pair of 2 different telescopes. We measure the amplitude and the actual images depends on the separation of the telescope and the orientation. So telescopes separated by large distances can give us an idea of the small scale in the images. And the telescope separated the smaller distances gave us an idea of the smoothness. So when we combine the spatial frequencies, we will get the image. Of course, ideally, we will fill the Earth with telescopes. Of course, we don't do this, but we use what is called the aperture synthesis, which is that we use the rotation of the Earth to track the visibilities between each pair of telescopes. Then we are tracking, these spatial frequencies over time. And of course, we are missing a lot of the spatial frequencies. So for us, making an image is like, imagine that you hear a song playing on a piano that is missing a lot of keys. So there are many keys that you don't hear. But if you have enough notes, you will recognize the song. So we are doing basically the same. We have very limited information, but we use this information, the properties of the source, to determine the final image that we see. So this is the way the EHT works. And here's another, oops, go back, another example of how it works. These are actual observations from 2017. You can see here the pair of image or the pair of antennas, and how, as we fill the information in the visibility plane, we can actually reconstruct the image by combining data, which is taken during a whole night of observation, taking into account that the Earth is rotating, and then capturing the spatial frequencies at different orientation in different distances. With this is how we get the final image. Let me explain a little bit more about how did we get the latest image from M7, because as you know, you have seen the image that we took in 2017, but we are taking observations almost every year. So we took observation 2018, 2019, 2020. We did not because of the pandemic, but then 2021, 2022, and so on. So the second observation of M7 took place in 2018, and we had an X antenna. So because of the X antenna, then we have a better sampling of the visibility plane. So we can do the Fourier transformation from the visibility plane to the image plane, and in principle get a more robust image, a better image. And this is what we did with these observations. As I said, a new antenna also, which had increased bandwidth, and but unfortunately the weather was not as good as it was for 2017. Let me also remind you that in radio observations, usually radio observations are not affected by atmosphere, and so you can take observation daylight even with clouds. But when you get into millimeter and sub-millimeter observation, it does affect our observation. So when we have clouds, this water vapor actually absorbs some of the emission. So we need to have good weather for doing these observations, and we need to have good weather in Chile and Hawaii and in the US and Spain and all the places at the same time. And as you could imagine, it's very difficult to have good weather all the time. So these observations are usually affected by that. In this case, for 2018, the weather was not as good as we had for 2017. So, and how do we actually produce these images? So we take the interferometric data, and then we do some image domain analysis and some analysis in the visibility plane of the interferometric data. And we have two different ways of doing this. One we call the inverse approach, and the other one is a forward approach. And we have been using multiple different pipelines for getting these images. Some of these are the standard clean imaging. This is the standard method used for interferometric imaging. And for the EHT, we have actually developed new methods, regularized maximum likelihood methods that actually minimize a function that compares the data with a given image. And also we have developed, especially for the EHT, bidirection imaging methods. And in this case, with these methods, we actually, given the data, we find the probability distribution of the images or modeled parameter. Let me remind you that for BLBI, I started doing BLBI in my PhD, and so for the last decades, it was just clean. So, and this was the only method. And now, actually, if you take a look at any interferometric data from ALMA, from Merlin, EBN, whatever array, when you have LOFAR, SgrA in the future, they are all using clean. And now we have developed just for the EHT these new pipelines, and this has produced a complete, and it's like a revolution in the field. We are getting images with significantly better angular resolution, and this has been possible thanks to the EHT. So with this method, what we have is a method that depends on some parameters or hyperparameters, and what we do, as I'm going to show you in a minute, we do millions of images actually from synthetic data, and we select what are the parameters, these hyperparameters for these methods that reproduce all the synthetic data sets. In the case of the Bayesian approach, this is not necessary because it's it's a procedural full sampling of all the possible images. Once we have the images, then we do the feature extraction. And once we have this image, we determine what is the size, what is the brightness asymmetry, or how deep is the central depression in the emission. And with all this, we do our science with the EHT. And we feed parameters, as I said, like diameter, brightness, symmetry, elasticity, and so on. And this is an example too. For instance, for the case of 2018 observations, we did a number of simulations. So these are these simulated images, using the same coverage, the same simulating an actual observation from the IAA-CSIC. So we say, okay, we are going to be observing during 12 hours this day, and these are the telescopes. So what kind of data we would expect if we were to have this kind of ring? This is a symmetric ring, a double, a this, and so on. And this last one is a GRMHD model. And these are the visibility amplitudes that we will get. In blue are the from the model, and in cyan or whatever, this orange color is for the actual M87 data that we took. And as you can see, for instance, they are images like rings and double that actually, if you look at the data, it would be actually difficult to distinguish whether it's a double or it's a ring. And we could be fooled, and we could think that what we are seeing is a ring, and instead of being a double. So this is why it's very important for us to actually use this simulated data and do all the different reconstructions with simulated data to make sure that we are not fooling ourselves, that we are not getting a ring when in fact, instead of a ring, it may be a double source, it may be a disk, or maybe a point source, okay? So, and this is what we do, and we have performed this with the different techniques, with the clean and the RML methods, as well as the validation methods. And as you can see here, we are actually able to reproduce and distinguish between different models, which give us the confidence that the final image that we have is the best reconstruction we could get from that data. So we are talking here about a million of images. Actually, for SgrA, we did something like 40 million images. To give you an idea, VLBI observations, you publish one image. So you get your data, you do your clean analysis, you get an image, and you publish an image, and that's it. We have done millions of, literally millions of images, mounting supercomputers, simulating everything, making sure that we are not fooling ourselves and we are not getting an image which is not the actual best representation of the data that we take. And let me just quickly, and yeah, okay. So, and this is the image that we got for 2018 data of M87, and you can see here, this compares with the image that we obtained in 2017. And yeah, here it's also just a comparison with the different methods. This is with the actual resolution of the methods convolved with a nominal resolution of 20 microseconds. You can see that all the methods give almost the same image, and also when we do the modeling of the data. So we are really quite confident that this is the best image that we have in 2018. And then we compare it with 2017. So of course, if what we have is the image of a black hole, we do not expect that the mass is changing over time in 1 year time scale. So we do expect to see the same size of the ring, and therefore, confirm the mass of the central black hole in M87. And this is what we did. So you can see here, we are comparing here what is the size and the position angle, the brightest section of the ring that we see in the image, and we compare data taken from 2017 and data taken from 2018. And as you can see here, these are the final values that we obtained. So the size of the ring diameter is very consistent. It's consistent between the two, very similar and consistent with errors of the two observations, 2017 and 2018. And this provides us the first confirmation of the image that we obtained in 2017 with a completely new, different data set. But we have noticed that there is a significant change in the orientation of the position angle of the ring. And do this image fit into the GR, and this is what we see. So this is the actual angular gravitational radius, so the mass over the distance for M87. And you can see here, using different methods in the two different epochs, we obtain a very consistent value, which is the size that you would expect for a 6.5 billion solar masses black hole in the center of M87. So this is exactly as predicted by GR. So this is the probability distribution for the mass obtained from the stellar dynamics, 6.5 billion solar masses, and this is the size measured with the ngEHT. So we confirmed at least that this is in agreement with GR. and a Kerr black hole. And why did we see some changes in the position angle? This is the image that we took in 2017 with the position angle basically pointing to the south. And in 2018, we saw a slightly different position angle for the brightest peak in the ring. And we have interpreted this as just being produced by the stochastic nature of the accretion into the supermassive black hole. And you can see here, this is, for instance, one of the GRMHD simulations that we are doing. So if you compute the GRMHD simulation and you blur to the resolution of the BHEX, you can see that just changes in the accretion of material around the supermassive black hole leads to these small changes in the position angle, and this is what explains this. Also, recently, last year, there was a paper in Nature also about MET7, where we saw that the jet in MET7 actually seems to be precessing. So a bit of these changes in the position angle that we see in the ring may be most probably associated with this precession of the jet in MET7. And what else? We took the first picture we measured for the first time. One is the magnetic field right in the vicinity of the event horizon in a supermassive black hole. And we published this in 2021 for MET7, and you can see here, and now we have this hairy plot that unfortunately looks a little bit like the hair of Trump, with this color and this style. But this is a natural representation of the magnetic field in MET7. This is the electric vector position angle. And as I said, we have determined, we have done some simulation and determined what is the expected position angle of the magnetic field of the polarization that we see in our observations. And this is this observation support a magnetic field which is mostly poloidal. So you have the black hole, you have the jet, and the magnetic field are basically poloidal and in the direction of the axis of the spin of the supermassive black hole. And actually, this information, polarization information, was key actually to constrain many of the parameters in our simulations. In a minute, I'm going to show you a lot of the GRMHD simulations, but here just let me show you two snapshots from two different models, what we call the MAT and the SANE models. The MAT are the magnetically arrested disk model, which means that the accretion disk is threaded by a dynamically important magnetic field. So you have a magnetic field which is quite strong. The material is trying to get into the black hole, but the magnetic field lines are pushing the material, and this preventing controlling the accretion into the black hole. And these strong magnetic field are the one that launch the powerful jet that we see in MET7. And you have here, this is the magnetically arrested disk, and the normal and evolution, the standard and normal evolution are called SANE, which is a weaker magnetic field and less efficient to generate the jet. And we have run the simulations. We have run it through the pipeline, generating the synthetic data. We have imaged that synthetic data, and these are the expected images that we will see with the EHT. And as you can see here, for the case of SANE, so weak magnetic fields, the polarization does not look like what we have seen. Only magnetically arrested models show polarization which are similar to what we see, and we did a full suite of many thousand GRMHD simulations, and with this we have constrained the parameters of the magnetic field in the supermassive black hole, and we think that this is a magnetic field which is dynamically important and controlling the accretion into the black hole, launching the jets, and it's a mild state. And we have done this also, and for SciJ. The previous image was MET7, and this is actually the polarization image for SciJ, and we just published this actually this year. And this, as you can see, is very similar to the polarization that we saw in MET7. So we see that the field lines, the electric vector position angle are following the ring in the jet. And when we do the comparison with the GRMHD simulations, again, for SciJ, we see a magnetically arrested disk that is around the central black hole in the galactic center. And let me show you now some of these simulations. For instance, this is one of the GRMHD simulations of magnetically arrested disks. This is with a given prescription for the heating of the electrons. This is with very high rotating black hole in different orientations. This is seen with 90 degrees to 10 degrees. So these are one of the simulations. We have played with different spin parameters. So you can see here retrograde accretion disk, a Schwarzschild black hole, prograde accretion disk. And we have been playing with different prescriptions for the heating of the electron formation. This is a parameter that we use and called RHI. And we have played with magnetically arrested disks and same models. So we have done thousands of these GRMGD simulation with the best GRMGD calls state-of-the-art in the community. There is nothing better than this GRMGD simulation we are doing. And we have done, as I said, thousands of different simulations in supercomputer. And we now have all these movies, and we compare it to the actual image that we got from SgrA. So in that sense, when you can start comparing, and for instance, the size that we see in the HT are some of these GRMGD models. The shape that we see for the image removes many of them when you take into account also the spectra and the expected emission like X-rays and the low frequency size. We are, removing many of these models do not actually agree with all the information that we have from SgrA. And at the end, this is the GRMGD simulation that best fit the image that we obtain in SgrA. And this is what we call the pizza plot. And this pizza plot shows the different parameters, so magnetically arrested disks, same disk, different prescriptions for the heating of the electron, different spin parameters, different orientations. And when you see that it's a red here, is that this parameter in particular do not pass all the tests, all the methods. And the only one that we saw that actually passed most of them, not exactly all of them, but basically, I mean, all of them, but not, as I said, because they are a little bit more variable than what we expected. And after analyzing 1.1 million images, 1.3 million LCDs, 50 terabytes of data, the best model that we have for SgrA is that it is a model with a magnetically arrested disk with a prograde spin, 50 degrees inclination, and this prescription for the heating. And look at the inclination, it's 30 degrees. This is unexpected because we expected there would be something like 90 degrees. So we would expect that the spin of the black hole will be perpendicular to the galactic plane, but it doesn't look like this. And actually, this is agreement with what gravity is observed. So it pays off. So we have beautiful pictures, but actually we can actually do some interesting science with these pictures.
So
yes,
the value, the sign of the spin.
Yes.
So that's with respect to the rotation of the galaxy, or with respect to the line of sight?
Yeah, it's an arbitrary unit. It's an arbitrary unit. Actually, positive. We say that it's a positive when you have the accretion disk and the black hole rotating in the center. This is the problem. And the maximum, it's 1, and then we have the retrograding, which the black hole is rotating to one side, but the accretion disk is rotating on the other side, which may be possible. So this is what we have so far published. So what is the next big thing for the field? And actually, this is something that I'm very happy to say that we are leading this from my institute, from my group, together with another group in Harvard and another group in Radboud University, and is to obtain the first movies of black holes. So we are now reaching a state-of-the-art of analysis of the data, in which we want not just to take images, but we want to actually take movies and understand really how accretion works into supermassive black hole. But this is extremely difficult. I mean, as I told you, we did millions of tests just to show one image, and now we are trying to make a movie. So it is proving extremely difficult, and still, well, there's not a lot of information I can give you about this, but I can tell you that we think we are in the verge of getting the first movie. It may be that we have to wait for data from the later observation, like 2022 observation, 2023, We are now analyzing data from 2017, which was excellent because of the weather was really good. And we are testing whether we can actually get a movie, and we are in the limit. I'm going to show you just a teaser of the kind of new tools that we are using. Sorry about this. So we are doing. Let me show you the kind of state-of-the-art, VLBI dynamic imaging that we are doing. So, what is the situation with SgrA? The situation with SgrA is that, as I mentioned to you at the beginning, when we do VLBI, we need to integrate the data that we took during the whole observation. We take into account the rotation of the Earth. This is the aperture synthesis. Actually, Martin and I got the Nobel Prize in 1974 for just this, for determining that you can use the rotation of the Earth to get VLBI images to synthesize enough information in the visibility plane to get this. So this is what we have used, and this is what we can use for MD7. But for SgrA, and this is another whole new presentation I can give it to you. This is extremely difficult. Why? Because SgrA is significantly smaller than MD7. It's 1,600 times smaller than MD7. It's very close, but it's 4 million compared to 6.5 million, which means that the light takes just about minutes, 4 times minutes, to go around the black hole inside. In the case of 77, it takes days to weeks, which means that we are observing the source for a whole night, say 10 hours, all right? And then the source is actually changing in time scale of minutes. So this completely contradicts the aperture synthesis that we are using. This, which is under the assumption that you integrate them during 10 hours and the source doesn't change. It's like, imagine you want to take a picture and you want to you need to do a long exposure picture of whatever. Imagine that you are taking a picture of a person and you say, okay, you remain still for 1 minute because it's low light, I'm gonna take a picture. And you get a pretty good picture. Now imagine that you want to do the same with a kid and the kid is moving around. What happens? The picture is gonna be completely broad, isn't it? So we have exactly the same problem. For SgrA, as I mentioned to you, I can give you a full 1 hour presentation of how we actually did that, because it was more than 1 year of effort to develop the techniques. But what can we do? We can actually try to develop dynamic VLBI imaging. We can try to use the information we have over time and to try to constrain a model that fits the data over time as the source is evolving. And this is what we are trying to do with SgrA. So, okay, well, this is what I mentioned to you before, that, the source is changing very rapidly. This is, for instance, one of the TMT simulations that I showed you before. This is how the UV plane is changing over time. So you cannot take just an image with just 20 data points. It's impossible. I mean, you don't have enough information. So you need to constrain a model that uses information over time. You need to correlate over different times. And for that, we have developed a new method. And actually, this is from my students, from Maria Porti, which is my student, Antonio Fuentes, who is my postdoc. And we have developed a new method, which is called TINIM. And it's a dynamic imaging method that uses a coordinate-based neural network. This is well known in computer science and neural radiance field network. So I guess you saw the advertisement of the Nobel Prize this year, a couple of days ago. And bam, they gave the Nobel Prize in physics, which to me was like, wow, to computer science, which is neural networks. So it was given for actually this method to physics, which is a little bit strange. But in any case, this method is actually based on those neural networks. So, and what we have is a set of coordinates, which is space, time. We pass this to a neural network. The neural network produces images in total intensity, degree of polarization, circular polarization. So, and produce a sequence of images over time. We can take each one of these images and compute the Fourier transformation, the visibility plane, and we compare this information with the actual data that we have. And this is what we call the loss function. This is the function that we need to minimize. Then we use a Nobel Prize backpropagation technique in neural networks to actually change and adjust the weights and the biases of the neural network until at the end we get a neural network that has learned what is the best model for that particular data. Let me stress that these are not trained neural networks. You may have heard, for instance, a neural network that it has learned how to, do this. So you have trained with millions of data, and then you act, this neural network is very well trained to this whatever. We have not trained the neural network with actual images of black holes. So our neural network is not biased to seeing black holes in the image. It's only just an inference problem. In this case, is what are the weights, which is, what are the different parameters of a continuous function, which is a neural network that actually produces the best fit of the data. Why is it powerful? Because many of the initial methods that we have do not, they need a prior initialization. Like let's assume that we have, how bad are we with time?
Not the time. The screen sharing stopped.
Oh, really?
For some reason, yeah.
Oh, sorry.
Something happened.
Let me.
Time we still have 15 minutes.
Okay.
So we started late.
Okay. Let me try to. All right. Okay. Super. So in this method, you don't need a prior initialization. You don't need a regularization. So you don't need to regularize your data over time or in space. And we only need to ensure that it's positive, that the image is positive, and the continuity and smoothness. And as I said, there's no training of neural network. And this is working really well. I'm very happy to let you know that I hope this is working. Yeah. Okay, let me show you just some text, some tests that we have done. This is the UV coverage that we have for 2017 data. This is very sparse. So imagine, we are missing 95% of the data that we need to get an image. But still, we can get an image with that amount of information. So this is a very limited, we are only covering this space in the Fourier domain. And this is a ground truth. This is a geometrical model, which is a ring with a hot spot going around. This is our simulation. And the simulation is composed of this ring with a hot spot going around. And this is the actual reconstruction from this technique. It is really quite remarkable. We never got anything as good as this. We can really recover the static part, and we can really trace a hot spot going around. So if there is a hot spot going around inside J, as gravity observed, we should be able to actually capture this with this technique. This is an idealized case, geometrical case, and things and so on. Then let me show you another example. For instance, this is a more complex case. This is a GRMHD model. This is the ground truth. So this is the simulation. This is a GRMHD model with a hot spot. And also, you can see here the characteristic of the scattering towards psi J, the galactic center. And this is the actual reconstruction that we are getting. And this is the dynamic component. So there is a hot spot going around, and actually, we can recover this with Kim. So why
was it changing color?
Sorry?
Why was it changing between color and gray?
Let me go. I didn't get the color. What? So. Yes. Sorry, I forgot to mention this. Yeah, the gray is when we do not have data. So it's like interpolating. Okay. And the red is when we actually have the data. Okay. Excellent question. And this is another example which is mainly meant for VLBI people. People that I'm not sure you are, you have in the field, but if you are in the field, you have been doing images of jets in supermassive black holes. These are the kind of images we can get now with this technique. I should have put in a comparison with the regular method with clean and so on. And this is really, it's like a complete different league. We are getting super resolution and a level of detail truly amazing for some of these. These are jets. These are actually 116 observations. This is something like 20 years of a jet in one of these blazars. This is a famous radio galaxy that is changing over time. In this case, it's 40 epochs covering 10 years of observation. And this is actually EHT observations, M87. And this is 4 epochs, so 3 epochs sorry, 4 epochs taken during 2017. And you can see here, we did, as I mentioned to you, millions of images with the different techniques. With this technique, I mean, this is just, it's straight, in one day you get this, and you get the evolution over time. So let me go to the last part of the talk. So I show you that we have taken the picture of black holes. I show you that they are consistent with the ER. I show you that we are trying to get the first movies. But how good is going to get the EHT? We are going to get something significantly better for the next 5-10 years. And this is actually what we are trying to do. And actually, we met 2 years ago in Granada to discuss this. What is the future of the EHT? And just to put it in perspective, these are the state-of-the-art in next generation astronomy. We are talking about SgrA, ALMA, GLA, James Webb, and Extreme Large Telescope. So you can see here what are the angular resolution and the frequency at which all these different state-of-the-art facilities we're going to have in the next decade. And this is where the EHT sits. It's the only instrument that can actually take images of black hole, and it's going to remain like this for at least for the foreseen future, for 10-20 years. But we want to get this even better. We want to get an even higher angular resolution and more dynamic range and extend to other frequencies. And for this, what we are submitting an 18 million proposal to a National Science Foundation in the US. And this proposal considers adding 4 different new sites, new antennas. Actually, one of them in Canary Islands in Spain, in Mexico, Las Campanas, in Wyoming. We are upgrading the instrumentation with different telescopes. We are doing multi-band observations, including more frequencies. All the observations that I showed to you were obtained at 230 gigahertz. We are adding 86 and 345 gigahertz, high bandwidth. We are going to implement a key technique, which is called frequency phase transfer, to actually get better sensitivity at very high frequencies. With this, in any case, what we are going to get is a factor of 5 increase in the Fourier spatial frequency domain. So we are going to get 5 times much better data. We are going to be able to get images, just instantaneous snapshot images of psi J. We are going to do long-term imaging of M87, and we are going to see more black holes. Just to give you an idea, this is the time scale and spatial scale that we are now observing with the EHT. We can distinguish things that change in 2 hours up to weeks, 20 microseconds to 200 microseconds. We are going to add 345, so we are going to increase our resolution to about 15 microseconds. We are adding to 86 gigahertz, so we are going to see more extended emission, and we are going to be observing during more time, so we are going to be able to see changes in seconds to months inside J and M87. This is just a simulation. This is a simulation of the jet in M87 with the current EHT and what we are going to be able to see in 2030. So we are going to be able to get, not only the ring, but also the jet at M87 in polarization. We are going to be able to determine what is the way we are extracting energy from the black hole to actually produce these amazing jets, which is the black holes 9. Since we have more antennas, we have a better instantaneous coverage in the UV plane, and we can actually get the first snapshot images of psi J. So we are going to get, now we are struggling to get a movie. We are going to now, in the next year, we are going to be able to get absolutely fantastic movies of black holes, and in particular of psi J. We are aiming not only to the psi J and M87, so we want to actually observe more targets. With this array, we have more sensitivity, and we can, for the first time, estimate the sizes and even through linear polarization, get an estimation of the spins on more sources. And actually, with this, we can do a population level spin measurement to distinguish what is the nominant growth of supermassive black holes, which of course is of extreme importance. And we are going to get much better tests of GR. With this, we just measure what is the size and how deep, how black is the inner ring or inner shadow. We can actually perform much better tests of GRs. I'm not going to get into the details, but with this, we have a precision which is of the order of 10% to test GR. With this, we are going to get significantly better than that. And also, we may be able to hopefully determine also the spin inside J. There's a very interesting trick in the polarization of these black holes. As I mentioned to you, we have a direct image, N0 image, and this is the polarization. But for the photon ring, for those photons that go around the black hole, the polarization actually is in the other direction. So we can actually try to distinguish the polarization from the direct image from the photon ring. And with this, actually, we can get an estimation of the spin of the site. Yes.
So what is the sort of polarization? Why? Well, so it's a scattering in electrons, right?
Yeah, exactly.
So why is the perpendicular?
Because it's going in the other direction. So you have one which is the direct emission, and the other ring is the photon ring is actually going all around the black hole, and that probes a different magnetic field and then twists the polarization. And not only that, you have all the lensing produced by the gravitational field, and that leads to a different polarization. So, yeah. Yeah. So it's basically it's a GR effect. So we are actually measuring GR there. We are measuring the lensing produced by the gravitational field, which changes the polarization.
So
the lensing
changes polarization.
It changes the polarization. And this is so as I said, then you have this is the polarization direct, this in the other, and then you would expect to see this change. But no, this not only this, we are now also proposing to NASA, and actually a Global Space Flight Center is supporting this mission, which is a mission, it's a SgrA mission by NASA to actually do a space BLDI, to put one of these antennas of the ngEHT in the space. And this, of course, it changes dramatically because the angular resolution depends on the separation of the antennas. And now we are not bounded to the Earth. We can put an antenna significantly, farther away. This increases the baseline, and this is going to give us a completely new view of this object.
Would you like to put one in the moon?
Yeah. Actually, there is a proposal for that. Yeah. So we do expect, and ideally we will put more than one. This is not a very expensive mission. This is how we're talking about SgrA mission, which is around $40–50 million. So it's, for NASA, this is a bit like peanuts. So hopefully, and what we are dreaming is something like ALMA in space. So meaning that you have multiple antennas in space. One of the difficulties, as I mentioned to you before, is that with our observations, we are subject to the weather. So if there is a bad weather, we don't get any data actually. So if you put it on the space, the quality of the data that we have is amazing as compared to what we could get. But this is significantly more expensive. But this mission, the interesting part is that if you have a ring, this is the beating that you expect in the visibility amplitude on separations between telescopes, which is of the size of the Earth. But this beating continues along longer baselines. So if you have longer baselines, you have a beating, and then this beating, at some point, you just don't see the N0, you just see the very thin ring. And this is the one that we really want to see. As I mentioned to you before, this is what we are seeing now, which is mostly dominated by the astrophysics. So our precision to test the GR is of the order of 10%. And when we start getting the actual thin ring, this thin ring, it encodes, it doesn't have any astrophysics. This is like observing the pure metric. So we can actually distinguish what we call the shape of the horizon changing with the spin. As it spins, and then it's not symmetric anymore. It's not circular anymore. When the black hole is spinning really fast, it's a little bit distorted. And this actually tell us what is the actual spin of the source. So this NASA mission, we are selling it as it is, which is the first time we will actually see the photon ring, the one that carries the metric, not just the astrophysics, but the metric, and the one that will tell us with a 10% precision the spin of Site A and M87. So we will be able to say, is the spin is 0.75 or whatever it is, with a 10% precision more or less. And this is mission led by PI Michael Johnson in Harvard. It's a 4-meter antenna, which well, I'm not going to give you all the details here, but this is simulated data, and you can see the beating and how we will be able to see the ring. And as I said, the main science goal is to, for the first time, see the length photon ring in one of the sources and make a direct measurement of the spin of the black hole. And actually, with this mission, we can see not only M87SJ, but we expect to see many other sources. We will be able to do to start doing some statistics about these black holes and to observe like 10, 20 other sources. And I think this is a bit too technical. I'm going to go very quickly. I mean, of course, it's not the first time we have done space VLBI. This is an example, and I have been working on this for my last 10 years, more or less. And this is another space VLBI mission. Actually, this was a Russian-led mission. Now it's like, you know, it's, you cannot imagine that working with the Russians, but we were working with the Russians. And it was very nice, and everything was working well. And this was a Russian mission, and everybody was using it. And, you know, it should be in science. And we were getting amazing images. And let me show you here first. This is one of the the best well-known source in one of the best studied blazars, AGNs, which is 379. It has an amazing jet. These are ground images at 7 millimeters, then 3 millimeters, so using a little bit. And this is actual image we got with the EHT. This is a supermassive black hole sitting here. This is the jet. This is 1.3 centimeter, and this is an angular resolution of the other 20 microseconds. So we actually observe this also with the space VLBI, and I'm going to compare you the image that we got with the EHT. This is actually regular ground-based VLBI 43 gigahertz compared to the 1 millimeter. So you can see here different resolutions. These are at the actual same scale. And we took the image with regards. This is the UV coverage that we got. So in principle, we have an angular resolution of the other 27 microseconds. With the same resolution as the ground array, this is what we saw. And this is how it compares with the EHT 1 millimeter. But when you put the actual glasses of the actual resolution that we got with this image, which is not this one, this is the ground base, then you zoom in into the actual image with space VLBI, and you can see that we got a completely different new picture. And this is just 1.3 centimeter. This is 10 times worse, 10 times worse than what we expect with BHEX. And even with this, you can see that it's significantly better than the ground array, and we can compare with the actual EHT, but even we were able to measure, you know, for, you know, longer distances with higher dynamic range to get the result. So with BHEX, we will get even something like 10 times better. So it's going to be very interesting for AGNs, and I'm not going to give you, this is another 1 hour call talk about you know, AGNs and how jets are produced, but there are many different questions. I think one of the most important questions is that we have these supermassive black holes, and these produce these amazing jets, like the ones I'm showing to you. We still don't know how they are produced. So these are the most energetic objects in the universe. A supernova is, you know, it's amazing for just 1 second. You know, it becomes brighter than the whole galaxy for 1 second. These guys, you know, they are active for the Hubble times. And that produces a huge amount of energy. And all this is coming from the central black hole. Most of the optical emission is produced by the accretion disk, and most of the internal energy is converted into radiation. But these jets, which I don't know if you saw, like there was a paper like 2-3 weeks ago, or 1 month ago in Nature, they have observed the longest jet ever. There's a megaparsec jet, you know, it's extending, you know, distances. I mean, it's like extending like the size of the Milky Way like 200 times. These guys are actually determining how galaxies evolve. They are actually determining what is the composition, the changes in the intergalactic medium. These are beings, and we do not know yet how they are getting all the energy. We think that they are tapping the rotational energy of the central black hole. So we think that the spin is relatively high, And then the magnetic field anchored in the ergosphere are trying to slow down the black hole. So they are getting the rotational energy, and it's being transporting the magnetic fields, and it's being transporting this jet. But this mission, we expect to actually be able to determine that. And there are many other important questions that, it's still after decades, we don't know. So with the BHEX mission, as I mentioned, we are going to observe many other targets, not only M87SIJ, but also we are going to do black hole demographics and study galactic from many other sources. And just to finish, so these are the images that we have. I think it's quite remarkable how similar they look like, and they are completely different in objects. This one produces one of the most amazing jets. This jet was observed in 1918 by Harvard. So this jet is well known for more than 100 years before we knew there were galaxies. And the guy was looking at these galaxies, and he saw that, what the fuck is this? And it was a jet, and it's well known for 100 years. It's an amazing jet. SGA does not have a jet, at least not one that we have observed. We don't have the angular solution, but they look really similar, as you can see. 5.5 million years. So this image is what the source looked like when the dinosaurs were running on Earth, and this is all like 27,000 years ago. How SGA looks like 6.5 million, 4 million, and the summary slide, which is, as I mentioned, we have now the SGA and M87 images. But as I show you, all this with the ngEHT, we will have ngEHT, the next generation ngEHT, we will have the Black Hole Explorer, the Space Builder mission, and this we will get a much better test of GR. We will understand how we can extract energy from black holes. We will understand the accretion, black hole demographics, multiplexing connection, IGN population. So this is going to produce really, I think, an amazing revolution in the next 10, 20 years of our understanding of supermassive black holes. And hopefully we will be able to, help with you. You are working here on gravity, on how gravity actually works. Hopefully these missions will for the first time actually provide significantly more precise test of GR really at the event horizon. These are supermassive black holes, so the curvature is not so large. It's not like the stellar mass black holes, but still, this is the closest we could get the actual event horizon. And I'm very happy to take any questions.
So we're a bit over time, but we'll maybe take a couple of quick questions.
Thanks.
So, the next question. You mentioned that given the change in interpreted stars faster than the M87 black hole, that it's more difficult to make this movie you're talking about.
Yes.
Would it be easier to make the movie from M87?
Yeah, absolutely much easier. And I think it's an excellent question, Alex. For the M87, it would be as easy as take multiple images every week. Just as easy as that. Very simple. The thing is that making one of these is hugely expensive. So you have to put in to coordinate 8 telescopes. These are state-of-the-art telescopes. We are leveraging billions of dollars in facilities around the globe, and each one of these observations is 10 petabytes of data. So it take us in more than 1 year to correlate the data and to do the analysis and everything. And this is for getting one image. So it's extremely expensive in time, in human resources, and also we need ALMA. And we are discussing with ALMA because ALMA is the most sensitive array in the ngEHT. We are discussing with ALMA the possibility of performing this observation. Now, ALMA only give us 10 days, usually 10, 20 days a year for observation. And actually we don't use all the time. So they give us a window, something like 10, 15 days, and we observe like 4 or 5 times with the best weather. And this is the period for BLDI for ALMA. There's nothing else. You cannot observe whenever you want. Now we are negotiating with ALMA to actually try to get these observations for running for 2-3 months, observing every 1 or every 2 weeks. So it will be extremely easier technically, but very expensive. But this is exactly where we are trying to do.
So when one compares the image of M87 and St. Louis A star, we see that St. Louis A star has like 3 bright spots, whereas M87 has 1. So what are these 3 bright spots?
That's an excellent question, and I wish I could tell you, because I don't know. Right, it's an excellent question. I mean, the thing is that getting the image of SgrA, as I told you, I can give you another 1 hour presentation. And so I'm not confident that these 3 spots are real. So it may be that this is just an artifact of the image. Actually, for SgrA, we took something like, 2,000 images. They are very similar, but they're slightly different. And all of them actually are consistent with the data. And even for SgrA, we have images that do not look like a ring and are also consistent with the data. Right? And we cannot rule them out because they are actually consistent. Excellent question. And I hope I will be able to answer you in, I don't know, a few years from now.
The images are consistent with the data.
Exactly.
It's hard for me to understand it, but when I thought that the images are the data.
It's not
So
as
what do you mean?
yeah, that's an excellent question. That's another very good question. It's not as I mean, taking an image with the LBI is not like taking an optical image with a CCD. So in an optical telescope, you actually just just record the data CCD. But here it's not. Here what we record is a visibility, is a Fourier transformation of the image. It's like imagine that you take a picture with your phone, and then I give you the Fourier transformation of that image. This is what we actually record. We do not record the image. We record the Fourier transformation of the image. These are the visibility. And for what you will call pixel, for us it's a given separation, given baseline, and that is a given spatial frequency. We record that. And then when we record that, we need to do the Fourier transformation to that to get the image. If you have a complete coverage, you only do a Fourier transformation, and this is a linear function. You have your data, you do a Fourier transformation, you get the image. You can ask that the write this for you in 1 minute, right? And that will be that's the image and that's it. But now we are missing. This is what I mentioned before. It's like imagine that the data we are recording is in nodes in a piano. But since we don't have antennas all over the world, we only have 2 nodes in the piano. The piano is missing a lot of things. And then we play the piano and we get some notes. And we need to figure out what is the song that is consistent with the notes that we are hearing. And this is why we need 10 million images a day. Because if you have that piano and you are missing a lot of things, then maybe 10 million songs. But you give this song to anybody, and then your ear will be very easy to say, oh, this song sounds, it doesn't have melody, and then you exclude that. Or it's like imagine that we are doing a jigsaw puzzle, and you have a puzzle of parts, and there are many different pieces, but you're missing a lot of them at the same time. And then you try to fill the gaps, and you wouldn't put a tree on top of a tree, no? So we are using that kind of criteria, something that is obviously wrong. We don't take it. So in that sense, what we get is an image that is consistent with the data, but there are an infinity number of images that are consistent with the data, literally an infinity number of images. So it's a completely impossible problem because we are missing a lot of data. And this is why getting these images is extremely difficult. This is why it takes 400 people in years, all these telescopes, trying to get these images. And when I tell you, for SgrA, as I was telling you, I don't think it's for the real. And we have actually something like 1,200 images that are consistent with the data. Most of them are rings. They're 90% of them. But it's a pretty decent thing. And as I say, imagine now we are not trying to just get images, we are trying to get images. We are getting into almost magic.
If you enjoyed the video, like and subscribe.